So we're going to have our function generator plugged into a capacitor and an inductor and a resistor. We're going to clip the alligator clip to the ground right here. We're going to set up two probes, one that's just going to be across the capacitor right here so we can measure the voltage, and one that's going to be across the total RLC circuit. We're setting the capacitor to 25, and then we're going to set the resistor to 50. Now we're setting the function generator at a square wave over here, a 10 frequency. So on our screen we have our two channels. Channel 1 looks more like a square, and channel 2 has some oscillations that are damping. So we want the voltages of the two lines to be the same, as you can see at the bottom there, 5 volts and 5 volts. And then we want to try to align these up together and get them to be right on top of each other. Do that. We're also going to set a voltage line right in the center there so we can line it up properly. So we're going to try to set the time equal to 0, being at the very top of one of those peaks, and then the second time will be to the next peak. And we're also going to measure the amplitude by setting the cursors right there at 0 voltage, and then the other one we're going to bring that to the top of the lines. So for time equals 0, we got 9.5 volts. On the second peak, we got 6.8 volts. And then for the time, it was actually 256 microseconds. For the last point, we have time as 1.02 milliseconds and the amplitude as 2.4 volts. Now those points gave us a exponential voltage versus time graph, which we could take the logarithm and calculate the slope of this line. Now from the graph, we can see the points are 256 milliseconds apart, and that we can see how close we were to the resonant frequency. We're also going to set the capacitor to 50. So now what we're going to do is we're going to try to fully damp this. Now because it starts off negative, what we're going to do is we're going to try to smooth this curve so we get nothing going positive. If there's anything going positive, then it looks like a pretty decent one. So at around 1900 resistance, we got a very nice curve here that looks like it's not going above at all. Well, according to our calculations, the correct critical damping resistance should have been 2245, and we were pretty close with that. Well, 1976 really is the total. We got a little error. We're going to set the capacitor to 0.3 microfarads and the resistor at 3000 kilo ohms. So we're now going to connect a multimeter between this point and that point to register the voltage that's going across both of these two.
Find as at maximum, it's at 0.15. If I keep turning it to the left, it'll decrease until around here it hits 0.12. If I turn it any further, it'll jump back up to 0.13 because the lowest value is 0.12 at 1157 hertz.
Our experimental frequency actually matches exactly with the calculated resonance frequency. We're going to first measure the voltage across the resistor, which is 6.55 volts. Then we're going to measure the voltage across the inductor, which is 0.99 volts. Then we're going to measure the capacitor voltage, which is going to be 0.95. And as we measure the total voltage of the resistor and the inductor and the capacitor together, we actually get 6.73. Now we're going to set the frequency to be half of what we had found at the resonance, which was 1157, bringing this down to about 55.7 or something. This time, as we measure the voltage across the resistor, we get 6.46. And as we measure the voltage across the inductor, we get 0.51. As we measure the voltage across the capacitor, we get 1.96 volts. And the total for all of this is going to be 6.79 apparently. Now you might have noticed that these voltages didn't really add up if you added them just like that. So we actually have to use the Pythagorean theorem like this because those voltages are not in line with each other. They're phase shifted. The cool thing is at resonance, the voltage across the capacitor and the inductor will be equal but opposite, so those will cancel out. And then the voltage from the resistor and the generator are going to be essentially the same. But at half resonance, you can see there's a phase-shifted angle here. But if we do this right, this component, the Y component, should match the voltage across the resistor.